Today in this video, we're going to be taking a look at a more complex projectile motion problem. So I'll read the problem to you. If you want to follow along, I've included the problem in the description of this video. So Bart decides to jump Springfield Gorge on his skateboard. Springfield Gorge is 50 meters wide, and Bart has constructed a 1 meter high ramp that is inclined at 30 degrees to the horizontal. If air resistance is neglected, calculate what speed Bart must reach if he is to land safely on the other side. So in short, we have to figure out what Bart's initial velocity has to be going off of this ramp for him to land safely on the other side, or for him to travel 50 meters along the x-axis. So a great strategy to approach complex physics problems, or any physics problem in general, is to make sense of your diagram. The way you can do this is by writing down all of your given values. So here I just wrote that I wrote VI because we don't know what it is. That's in fact that's what we're looking for. That will be the answer to this question once we figure this out. But I've labeled VI as the initial velocity that he will be launching off the ramp with. So what do we know? What are we given? Well, the displacement along the x-axis will be 50 meters because we're trying to figure out what VI has to be for him to get here. And for him to get here, he will have traveled 50 meters on the horizontal axis, or the x-axis. So I'm going to write displacement along the x-axis equals 50 meters, okay? We can do a similar thing for the y-axis. So the displacement on the y-axis, just caring about what's happening vertically, he starts at 1 meter above this ground level, and then he lands at the ground level. So he will have traveled 1 meter down, or -1 meters. What else? We know obviously the acceleration along the y-axis is -9.8 meters per second squared, because that is the normal acceleration due to gravity. So and in the problem description it said neglect air resistance, so the acceleration along the x-axis will be 0. What else? We don't know the time, so I'll just write over here, we don't know the time. And okay, so we can now write our initial velocity in respect to just a general VI. So we don't know what this value is, but we do know that whatever this is, it's going to be VI times the cos of 30. Because whenever you have the hypotenuse and an angle, the horizontal component of that will be the hypotenuse times the cos of this angle, and the same for the vertical component, except it will be VI times the sine of that angle. So I'll just write those down right now. The initial velocity along the x-axis is going to equal VI, whatever that is, times the cos of 30 degrees. And over here we have VIY equals VI sine 30 degrees. Okay, and we don't care about the final velocity because the question doesn't specify for that. These are all the variables that we care about, and here they are. So now that everything's written down and in front of us, we can start to figure out some equations that we want to use so that we can find our initial velocity that Bart needs to reach to safely reach the other side. So the first thing I notice when looking at all of the variables I have here is that the time variable is going to be the same for both the horizontal variables and the vertical variables. So what I'm going to do is I'm going to solve for time on one side and then sub that value into the other side, and hopefully we can figure out some stuff. Alright, so since we have 0 acceleration here, it's going to be much easier to solve and isolate for the variable time. So that's what I'm going to do first. So using the horizontal variables, I'm going to isolate for time. So I know that always the displacement of something is going to equal its velocity times the time taken. Okay? That's like one of our standard definition equations. Okay, so now I can use the values I have. I have delta D along the x is 50. And that equals the VI at x, which is VI cos 30, times the time, which we don't know. And since we're isolating for t, I can divide both sides by VI cos 30, and then I'll isolate me for time. So t equals 50 over vi cos 30. Hopefully this was pretty clear. Now we can use this value, delta t, and use it in an equation for the vertical variables. All right, so what is an equation that uses both displacement, acceleration, initial velocity, and time? Well, that would be this equation. Delta d equals vi delta t plus 1/2 of acceleration delta t squared. All right, this is the equation that we want to use, and now we can sub in our delta t variable for all of these delta t's and solve for vi. So delta d, I'm just going to keep it as delta dy for now. VIY is VI sine 30, and delta t we can sub in, that is 50 over VI cos 30, and then plus 1/2 of acceleration, so plus 1/2 of acceleration along the y-axis, and then that's all delta t squared. So again, 50 over VI cos 30 squared. Okay, this may look like a lot. All I've done here is changed VI for VIY, which is VI sine 30, and all the times that I had delta t, I just put in the delta t that we found above using our horizontal variables, okay? So now we have a messy equation, and we're gonna have to solve it. All right, so just so you know, though we do know the value of d and a, we're not gonna sub them in yet because I'd prefer to simplify this messy equation that I have here first, and then add in more numbers, just so I don't get overwhelmed with numbers and it gets all messy, all right? So the first thing I notice is that we have a VI on the numerator, a VI on the denominator, so those can be crossed out. Also, sine 30, I can plug in sine 30 divided by cos 30, because we have a sine 30 over a cos 30. That equals 1 over root 3. So we'll have 1 over root 3 times 50. Well, that'll just be 50 over root 3, okay? So equals 50 over root 3. And so this whole complicated section is just 50 over root 3. And then we have 1/2 of ay, which is a is negative 9.8, so I can just make that negative 4.9. So minus 4.9. And then we're squaring this, so 50 squared is 2,500 over this squared, which is going to be VI squared times cos squared 30. Okay. Oh wow, I was smudging this, sorry about that. So as we have it, also dy is negative 1. Okay, so that's our next line. From this, what can we do? We could subtract 50 over root 3 from both sides. So we'll have negative 1 minus 50 over root 3. That equals negative 4.9 times 2,500 equals negative 12,250. So equals negative 12,250 over VI squared, and cos 30 squared is 3 over 4, so 0.75. Okay, now we can simplify this side because negative 1 can just be rewritten as negative square root of 3 over square root of 3. Right, because anything divided by itself is 1, so this is the same thing. And then we have a common denominator, so we have negative root 3 minus 50 over root 3. Okay, so that's how we simplify that side. Also over here, we have we can divide negative 12,250 divided by 0.75 to simplify this section, and we get negative 16,333.3, which just goes on forever, okay? And that is over VI squared. Okay, so now we have a basic equation. We have a fraction equals a fraction. So we can do cross multiplication, right? So this numerator times this denominator equals this denominator times this numerator. All right, so this number times the square root of 3. Whoa, that's complicated. So I'll just write negative 16,333.3 forever times root 3. A lot of 3's on this side. Equals vi squared times this. All right, so this is what we have now. Already looks much better than what we had before. I can divide this bracket from both sides to isolate for vi squared. So doing that, I'll have negative 16,333.3 root 3 over negative root 3 minus 50 equals vi squared. And then if I just find the square root of both sides, that'll be vi. Okay, so vi. Now you got to be careful that you don't mess this up on your calculator because it's pretty complicated. So I have the square root of negative 16,333.3 is going on forever. So I'll just do 1 over 3 times the square root of 3. All of that divided by negative root 3 minus 50, okay? And that gives me 23.385. Okay, this is the magnitude of our initial velocity. So that is the problem. It was quite complicated. So, in conclusion, Bart needs to go at least a speed of 23.385 meters per second to clear this 50 meters. Yeah, it's a complicated problem because we have to deal with a lot of square roots, a lot of cosines and sines. Yeah, but if you ever run into problems like this on evaluations or in assignments, what's really important is that you just take it step by step. If I skip some steps for you, maybe you want to take a little bit slower and not combine steps and just have a really long page and take a lot of time, but that's okay, as long as you get the right answer and don't make any errors, then you'll be good. So hope that helped.